Hello and welcome to Late Physics. If you enjoy slow, thoughtful journeys into the deeper layers of reality, consider liking the video and subscribing to the channel. And as you settle in, I'd love to know, where in the world are you watching or listening from tonight? Perhaps from a quiet room, a dimly lit space, or somewhere far away under a different sky. Wherever you are, the same underlying fields we'll be exploring tonight are there with you too. Take a moment to get comfortable, because what we're about to explore is not just a story about physics, but a quiet rethinking of what reality itself might be. For most of human history, the world has seemed solid and dependable. Objects appear to sit firmly in place. Surfaces feel smooth or rough beneath our fingertips. The ground beneath us feels stable, unmoving. It is natural to assume that what we see is more or less what truly exists. But over the past century, physics has gently, and sometimes quite dramatically, shifted that perspective. Beneath the surface of everyday experience, scientists have uncovered a very different picture, one in which solidity dissolves into structure, and structure dissolves further still into something more abstract, more subtle, and perhaps more beautiful. According to our best modern understanding, the universe is not fundamentally made of tiny solid particles. Instead, it appears to be woven from invisible fields. These fields are not objects. They're not located in one place or another. They do not sit inside space. They are space. They extend everywhere, quietly, continuously, filling what we once thought of as empty void. And what we call particles, electrons, photons, quarks, may not be independent things at all, but rather small ripples, fleeting excitations moving through these underlying fields, like gentle waves across an unseen ocean. Tonight, we're going to take our time with this idea. We'll move slowly from the familiar to the unfamiliar, from solid matter to atoms, from atoms to particles, and from particles to fields. Along the way, we'll explore how these fields interact, how they give rise to forces, and how they allow physicists to predict the behavior of the universe with astonishing precision. But we'll also step a little further. We'll quietly explore what this means, because if reality is not made of things, but of fields, relationships, and patterns of activity, then the idea of empty space begins to change. It is no longer empty, it becomes something active, alive with subtle motion, even in complete stillness. And perhaps, as we move through this journey, the world around you may begin to feel just a little different, not less real, but deeper. So wherever you are, whether you're watching, listening, or simply drifting off, let's begin gently and take a closer look at what quantum fields might be quietly telling us about reality itself. If you pause for a moment and simply notice the world around you, everything appears reassuringly solid. A table feels firm beneath your hand. A wall seems unmoving and dependable. Even the air, though invisible, feels like an empty backdrop in which everything else exists. It is easy, almost unavoidable, to assume that reality is built from solid things. Objects that occupy space, persist through time, and behave in ways that feel predictable. This everyday experience is not misleading in a practical sense. It works. It allows us to build, to navigate, to live. But it is also, in a deeper scientific sense, only a surface-level impression. The question we are quietly exploring is a simple one, but it opens into something much larger. What is reality actually made of? For a long time, the most natural answer was matter. small pieces of substance that combine to form larger structures. This idea stretches back through ancient philosophy, but it became far more precise during the scientific revolution. In the 17th century, thinkers like Isaac Newton developed a powerful framework for understanding the world. Newtonian physics described objects as having definite positions, definite velocities, and predictable interactions. If you knew the forces acting on something, you could calculate how it would move. The universe, in this view, was something like a vast, intricate machine. Newton's laws of motion, along with his law of universal gravitation, provided a clear and remarkably successful description of reality at everyday scales. Planets followed precise orbits. Falling objects accelerated in predictable ways. Even complex systems could, in principle, be understood by breaking them down into smaller parts and analysing their interactions. There is a quiet comfort in this picture. It suggests that reality is built from pieces, solid, well-defined components, and that by understanding those pieces, we can understand the whole. But as scientific investigation continued, this picture began to soften. By the 19th century, scientists had already begun to question what solid really meant. Experiments in chemistry and early atomic theory suggested that matter was not continuous, but composed of discrete units called atoms. These atoms were thought to be the smallest building blocks, indivisible and fundamental. And yet, even that idea did not last. In the early 20th century, experiments led by researchers such as Ernest Rutherford revealed that atoms themselves have internal structure. When alpha particles were fired at thin sheets of gold foil, most passed straight through, but a small number were deflected at large angles. This led to a striking conclusion. Atoms are mostly empty space. At the centre lies a tiny nucleus, containing most of the mass, while electrons occupy regions around it. So if an atom was scaled up so that its nucleus were the size of a small marble, the nearest electrons would be hundreds of meters away. Everything in between would be, in a very real sense, empty. And yet, despite this emptiness, matter still feels solid. This is one of the first gentle hints that our everyday experience does not directly reflect the underlying structure of reality. As research continued, the situation became even more subtle. Electrons, protons, and neutrons, once thought to be the fundamental pieces, began to behave in ways that resisted simple description. They did not act like tiny billiard balls. They exhibited wave-like properties, spread out in space, and could not be pinned down to precise locations without changing their behavior. This shift became clear through a series of experiments that now form the foundation of quantum physics. One of the most famous is the double-slit experiment. When particles such as electrons are fired toward a barrier with two narrow openings, they do not simply pass through one slit or the other as classical objects would. Instead, they produce an interference pattern, as though each electron behaves like a wave passing through both slits at once. Even more curiously, when one attempts to measure which slit the electron passes through, the interference pattern disappears and the electron behaves more like a localized particle again. It is not that the electron switches between being a wave and a particle. Rather, it does not fit neatly into either category. Already, the idea of solid, well-defined building blocks, is beginning to blur. The deeper scientists looked, the less the universe resembled a collection of tiny objects, and the more it began to resemble something fluid, probabilistic, and difficult to visualize. At this point, it is worth pausing and noticing something subtle. None of these discoveries make the world less real. The table is still there, the wall still feels solid, the ground still supports your weight. But the explanation for why these things behave as they do is no longer what it once seemed. The solidity you feel is not the result of tiny solid pieces packed tightly together. Instead, it emerges from interactions, forces, fields, and constraints that prevent atoms from passing through one another. In fact, the overwhelming majority of what we call matter is empty space, as structured by invisible influences, and this is where the shift begins to deepen. Classical physics, shaped by Newton's work, assumes that objects exist independently and move through space. Space itself is treated as a passive stage, an empty container in which events unfold. But as we move into modern physics, that assumption begins to change. Space is no longer just a backdrop, and objects are no longer the primary ingredients. Instead, something more fundamental seems to be present, something that exists everywhere, even where there appears to be nothing at all. To ease into this idea, it helps to think about familiar examples. Consider temperature in a room. You do not see temperature directly, but you can measure it at every point in space. It is not located in a single place, but spread continuously throughout the environment. Or think about a gravitational field. The Earth does not pull on objects only when they're close enough to touch it. Its influence extends outward, shaping the motion of objects at a distance. This influence can be described as a field, a quantity defined at every point in space. These examples begin to hint at a different way of thinking. Instead of imagining reality as made of objects sitting in empty space, we can begin to imagine space itself as filled with properties, structures, and patterns. At first, this may feel like a subtle shift, but it leads somewhere quite unexpected. Because if what we call particles are not truly independent objects, and if what we call empty space is not truly empty, then the distinction between something and nothing begins to soften. The world becomes less about things, and more about relationships, behaviors, and patterns, and as we continue, this perspective will gradually come into focus. We will move from atoms to something deeper, from particles to something more fundamental, from the idea of solid matter to the possibility that reality is woven from something continuous, dynamic, and quietly present everywhere. For now, it is enough to rest with this gentle uncertainty. The world you experience is real and stable, but beneath that stability, something far more intricate is unfolding. An understanding that deeper layer begins with letting go, just slightly, of the idea that reality is built from solid things. For a long time, it seemed reasonable to imagine that matter was continuous. If you were to take a piece of stone, or wood, or metal, and divide it in half, and then divide it again and again, it was natural to assume that this process could continue indefinitely, that no matter how far you went, you would always be left with smaller pieces of the same substance. This idea that matter is continuous and infinitely divisible feels intuitive. It matches everyday experience. When you break something apart, you do not encounter empty gaps or hidden structures. You simply get smaller fragments. But over time, careful observation began to suggest something different. In the early 19th century, a chemist named John Dalton proposed that matter is composed of discrete units called atoms. According to Dalton's atomic theory, each chemical element is made of its own type of atom, and these atoms combine in fixed ratios to form compounds. This idea helped explain patterns in chemical reactions. Substances did not combine in arbitrary amounts, but in precise repeatable proportions. Water, for example, always forms from 2 parts hydrogen and 1 part oxygen by number of atoms. Not 1.9, not 2.1, but exactly 2 to 1. This regularity hinted at an underlying structure. Atoms, in Dalton's view, were indivisible building blocks, small, solid, and fundamental, the final layer beneath everything else. And for a while this seemed like a satisfying answer. But as experimental techniques improved, scientists began to look more closely. In 1897, J. Thomson conducted experiments using cathode rays, streams of charged particles moving through vacuum tubes. By observing how these rays bent in electric and magnetic fields, Thomson concluded that they were made of negatively charged particles much smaller than atoms. These particles came to be known as electrons. This was a surprising result. If atoms contained smaller components, then they were not indivisible after all. To make sense of this, Thomson proposed what became known as the plum pudding model. In this picture, the atom was imagined as a positively charged sphere, with negatively charged electrons embedded throughout it, somewhat like raisins in a pudding. It was a creative idea, and for a time it helped organize thinking. But it did not last. In 1909, a series of experiments conducted by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden provided a very different picture. They directed alpha particles, positively charged particles, at an extremely thin sheet of gold foil and observed how they scattered. Most of the alpha particles passed straight through the foil as though it were almost entirely empty. But a small number were deflected at large angles, and a few even bounced almost directly backward. Rutherford famously remarked that this was as surprising as firing a shell at a piece of tissue paper and having it bounce back. The conclusion was unavoidable. Atoms are mostly empty space. Rather than being a uniform sphere, the atom consists of a tiny dense nucleus containing positive charge, surrounded by electrons occupying regions of space around it. To get a sense of scale, imagine the nucleus as a small marble placed at the centre of a vast cathedral. The electrons would be moving somewhere near the outer walls, leaving almost all of the interior space empty. And yet, despite this overwhelming emptiness, matter still feels solid. This apparent contradiction is one of the most fascinating features of the physical world. The solidity we experience does not come from tightly packed solid components. Instead, it arises from interactions, specifically electromagnetic forces that prevent atoms from collapsing into one another. When you press your hand against a table, the electrons in your hand repel the electrons in the table. This interaction creates the sensation of resistance. So what feels like contact is, in reality, a balance of forces acting across mostly empty space. Already the idea of matter as solid substance is beginning to dissolve. But the story continues, and with further investigation revealed that even the nucleus is not fundamental. It is composed of protons and neutrons, which themselves are made of smaller particles called quarks. These quarks are bound together by the strong nuclear force, mediated by particles known as gluons. At this point, the picture becomes increasingly intricate. Instead of a few simple building blocks, we find layers within layers. Each time we look more closely, new structures appear, new rules emerge, and the sense of reaching a final solid foundation begins to slip further away. By the mid-20th century, physicists had identified a growing list of subatomic particles. electrons, muons, neutrinos, quarks, and many others. Some of these particles are stable, while others exist only briefly before transforming into different forms. This collection of particles is organized within what is known as the Standard Model of Particle Physics. It provides a remarkably successful description of how these particles behave and interact. But even here, something curious remains. Although we refer to these entities as particles, they do not behave like tiny localized objects in the classical sense. They do not have sharply defined positions and trajectories in the way that Newtonian physics would suggest. Instead, their behavior is described by probabilities. They can exist in superpositions of states spread out across regions of space and only take on definite properties when measured. This raises a quiet but profound question. If these so-called particles are not truly solid objects, if they do not occupy precise positions, and if their behavior is inherently probabilistic, then in what sense are they fundamental? It begins to seem that the concept of a particle, while useful, may not be the deepest description of reality. To understand this more clearly, it helps to reflect on how these particles are detected. In experiments, such as those conducted at large research facilities like the European Organization for Nuclear Research, often called CERN, particles are not observed directly. Instead, they are inferred from the traces they leave behind, tiny bursts of energy, tracks in detectors, or patterns of interaction. What we call a particle is in many ways a pattern of behavior, a consistent, repeatable way in which energy and momentum appear in measurements. This subtle shift, from thinking of particles as objects to thinking of them as patterns, marks an important step. Because if particles are not the final building blocks, then something deeper must be responsible for these patterns. Something that exists even when no particle is present. Something that fills space continuously, rather than appearing only at isolated points. And this brings us closer to a different picture of reality. One in which the idea of matter as a collection of tiny solid pieces gives way to something more fluid, more distributed, more fundamental. The progression from classical matter to atoms, from atoms to subatomic particles, and from particles to increasingly abstract descriptions reveals a consistent theme. Each layer is less solid, less localized, and less intuitive than the one before it. It is as though the closer we look, the less the universe resembles a collection of things, and the more it begins to resemble a system of relationships, interactions, and underlying structures that are not directly visible. There is a quiet elegance in this unfolding. What once seemed simple becomes complex. What once seemed solid becomes structured. And what once seemed fundamental becomes, in time, something that points beyond itself. And so, the question remains gently open. If atoms are not the foundation, and particles are not the foundation, then what is? As scientists continue to look more closely at the behavior of atoms and their components, a quiet tension began to grow. The familiar rules of classical physics, so successful in describing planets, falling objects and everyday motion, began to fail in subtle but unmistakable ways. Light, for example, had long been understood as a wave. This idea was supported by experiments showing interference and diffraction, where light spreads out and overlaps in patterns that only waves can produce. The equations of James Clerk Maxwell, developed in the 19th century, described light as an electromagnetic wave moving through space at a fixed speed. This picture worked beautifully. And yet, at the turn of the 20th century, a problem appeared. When scientists studied how objects emit light, particularly the glow of heated objects known as blackbody radiation, they found that classical physics made incorrect predictions. According to classical theory, an object should emit an infinite amount of energy at very short wavelengths, leading to what became known as the ultraviolet catastrophe. Clearly something was wrong. In 1900, a physicist named Max Planck proposed a solution that was, at the time, more of a mathematical adjustment than a philosophical revolution. He suggested that energy is not emitted continuously, but in discrete packets, which he called quanta. This idea can be expressed simply. The energy of radiation is proportional to its frequency, such that energy equals Planck's constant multiplied by frequency. This was a small change, but it had enormous consequences. Energy, which had always been thought of as something that could vary smoothly, was now restricted to specific amounts. It could be added or removed only in fixed steps, like climbing a staircase rather than sliding along a ramp. At first, this idea seemed almost like a convenient trick, but in 1905 Albert Einstein extended this concept in a bold way. He proposed that light itself is made of discrete packets of energy, later called photons. This idea helped explain the photoelectric effect, where light shining on a metal surface can eject electrons. Classical wave theory predicted that increasing the intensity of light should increase the energy of the emitted electrons. But experiments showed something different. The energy of the electrons depended only on the frequency of the light, not its intensity. Einstein's explanation was simple and powerful. Light arrives not as a continuous wave, but as individual quanta. Each quantum carries a specific amount of energy. If that energy is high enough, it can knock an electron free. If it is not, as no amount of additional light will make a difference. This marked the beginning of a deeper shift. Light, once understood purely as a wave, now also behaved like a particle, and this dual nature was not limited to light. In the 1920s, experiments conducted by Clinton Davison and Lester Schirmer showed that electrons, long considered particles, can also exhibit wave-like behavior. When electrons are scattered off a crystal, they produce interference patterns, just like waves passing through a series of openings. This phenomenon is known as wave-particle duality. It does not mean that something is sometimes a wave and sometimes a particle. Rather, it means that our classical categories are not sufficient to describe what is happening. The underlying reality does not fit neatly into either box. Instead, like quantum objects are described by something more abstract, a mathematical function that encodes probabilities. This is often called the wave function. It does not tell us exactly where a particle is, but rather where it is likely to be found when measured. This introduces a new kind of uncertainty. In 1927, Werner Heisenberg formalized this idea in what is now known as the uncertainty principle. It states that certain pairs of physical properties, such as position and momentum, cannot both be known with arbitrary precision. The more precisely one is known, the less precisely the other can be determined. This is not due to limitations in measurement technology. It is a fundamental feature of nature. In clear terms, the uncertainty principle can be expressed as the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a small constant related to Planck's constant. This means that at very small scales, the idea of a particle having a definite position and a definite velocity at the same time simply does not apply. The classical picture begins to unravel. Instead of well-defined trajectories, we have probability distributions. Instead of certainty, we have likelihood. Instead of precise predictions, we have statistical outcomes. And yet, despite this apparent loss of determinism, quantum theory is extraordinarily successful. It allows physicists to calculate the behavior of atoms, molecules, and subatomic particles with remarkable accuracy. The energy levels of electrons in atoms, for example, are quantized. Electrons can occupy only specific energy states, and transitions between these states produce precise spectral lines. These spectral lines are so consistent that they can be used to identify elements in distant stars billions of light years away. The underlying rules may be strange, but they are reliable. Still, the philosophical implications are difficult to ignore. In classical physics, if you knew the initial conditions of a system, its position and velocity, you could, in principle, predict its future exactly. The universe was deterministic, unfolding according to fixed laws. Quantum theory challenges this idea. Even with complete knowledge of a system's wave function, you can only predict probabilities. The exact outcome of a single measurement remains uncertain until it is observed. This raises deep questions about the nature of reality. Is the uncertainty inherent in the system, or does it arise from the act of measurement? Does the wave function represent something physically real, or merely our knowledge of the system? Different interpretations of quantum mechanics offer different answers, but none fully restore the classical sense of certainty. One of the most famous discussions of this issue involved Albert Einstein and Niels Bohr. Einstein was uncomfortable with the idea that nature is fundamentally probabilistic. He is often quoted as saying that he believed God does not play dice with the universe. Bohr, on the other hand, accepted the probabilistic nature of quantum theory and argued that classical concepts simply do not apply at the quantum level. Their debates highlight a key point. The quantum theory is not just a new set of equations, it is a different way of thinking about reality. And as this new framework developed, it became clear that the concept of a particle, already under strain, needed to be reconsidered. If particles do not have definite positions until measured, if they can behave like waves, if their properties are described by probabilities rather than certainties, then perhaps the idea of a particle as a small localized object is not fundamental. Perhaps it is an approximation, a useful way of describing certain behaviors, but not the deepest level of reality. This realization sets the stage for a further shift, one in which the focus moves away from particles entirely and towards something more continuous, more pervasive, and more foundational. Something that exists not just at specific points, but everywhere. And in that shift, the familiar idea of matter begins to dissolve once again, making space for a different kind of understanding. There is a particular experiment in physics that feels almost like a quiet riddle. It is simple to describe, and yet it resists every expectation we bring from everyday experience. Over time, it has become one of the clearest windows into the deeper behavior of what we call particles. This is the double-slit experiment. Imagine a source that emits electrons one at a time, not a stream, not a burst, but individual electrons, spaced out so that each one travels alone. In front of this source is a barrier with two narrow openings or slits. Beyond the barrier is a screen that can detect where each electron arrives. If electrons were simply tiny particles like grains of sand, we would expect each one to pass through one slit or the other, forming two distinct bands on the screen. But that is not what happens. Instead, As more and more electrons are detected, a pattern gradually emerges. It is not two bands, but a series of alternating light and dark regions known as an interference pattern. This pattern is characteristic of waves. It is the same kind of pattern produced when water waves pass through two openings and overlap, reinforcing each other in some places and cancelling out in others. But here is the curious part. The electrons are sent one at a time. Each individual electron arrives at a single point on the screen. It does not spread out as a visible wave, and yet, over time, the accumulation of many single impacts builds up a pattern that suggests each electron somehow interferes with itself. This raises a very quiet but profound question. Through which slit does the electron pass? If it passes through only one slit, there should be no interference pattern. If it behaves like a wave passing through both slits, then in what sense is it a particle? To explore this, physicists introduce detectors to observe which slit each electron passes through. And when they do this, something remarkable happens. The interference pattern disappears. Instead, the electrons now form two distinct bands, as though they're behaving like classical particles again. The act of measurement changes the outcome. This is not a matter of disturbing the system in a crude way. Even when the measurement is as gentle as possible, the result remains the same. When information about the electron's path is available, the wave-like pattern vanishes. This phenomenon is deeply connected to the principle of superposition. In quantum mechanics, a system can exist in multiple possible states at once. Before measurement, the electron is not in one definite path or another. It is described as being in a superposition of paths, a combination of possibilities. Only when a measurement is made does one of these possibilities become realized. It is important to be careful here. This does not mean that the electron is physically splitting into two smaller electrons, or that it is literally travelling along two paths in the classical sense. Rather, the mathematical description of the electron includes multiple possibilities, and these possibilities can interfere with one another. The wave function, which encodes these possibilities, evolves smoothly and deterministically according to the equations of quantum mechanics. But the outcome of a measurement is probabilistic. This leads to a subtle distinction. The evolution of the wave function follows precise rules, but the results we observe, where an electron actually appears on the screen, are governed by probabilities. This is not due to incomplete knowledge. Even with a complete description of the system, the exact outcome of a single event cannot be predicted with certainty. Only the likelihood of different outcomes can be calculated. To put it simply, quantum mechanics tells us what can happen and how likely each possibility is. It does not tell us exactly what will happen in any individual instance. This probabilistic nature has been tested extensively. Experiments performed in laboratories around the world, including those at institutions like the Massachusetts Institute of Technology and the Max Planck Institute, have confirmed these predictions with extraordinary precision. The statistical patterns produced by quantum systems match theoretical calculations to many decimal places. So while individual events are uncertain, the overall behavior is highly reliable. Still, the implications are difficult to reconcile with everyday intuition. In classical thinking, objects have definite properties whether or not we observe them. A ball has a position and a velocity even if no one is looking. Measurement simply reveals what is already there. In quantum mechanics, this assumption no longer holds. Before measurement, certain properties do not have definite values in the classical sense. Instead, They exist as a range of possibilities, described by the wave function. This brings us to the concept of measurement itself. What does it mean to measure a quantum system? At its simplest, measurement involves an interaction between the system and a measuring device, but this interaction seems to play a special role. It is associated with what is often called the collapse of the wave function, where a range of possibilities reduces to a single observed outcome. Different interpretations of quantum mechanics attempt to explain this process in different ways. Some suggest that the wave function represents our knowledge, and that collapse reflects an update in information. Others propose that all possible outcomes occur, but in different branches of reality. What remains consistent across these interpretations is the experimental result. Our particles do not behave like simple objects with fixed properties. They exhibit behaviors that depend on context, on measurement, and on the structure of the experiment itself. Even the idea of a trajectory, a path through space, becomes uncertain. In classical physics, a particle follows a well-defined path from one point to another. In quantum mechanics, the concept of a path is replaced by a range of possible paths, each contributing to the overall behavior. This idea is captured elegantly in the work of Richard Feynman, who developed a formulation known as the path integral approach. In this framework, a particle does not take a single path, but rather explores all possible paths, with each path contributing to the final outcome. While this may sound abstract, it leads to precise and testable predictions, and once again, those predictions match experiment. At this point, the word particle begins to feel slightly misleading. It suggests something small, solid, and localized, something with a definite position and a clear identity. But the entities described by quantum mechanics do not fully match this picture. They are not simply objects. They are better understood as patterns of behavior, governed by underlying rules that differ from classical expectations. This does not mean that the concept of a particle is useless. It remains an extremely effective way to describe many phenomena, but it may not be the deepest level of description. There is growing sense that what we call particles are manifestations of something more fundamental, something that can produce both wave-like and particle-like behavior, and something that exists even when no measurement is taking place. And as this realization settles in, it invites a shift in perspective. Rather than asking how particles behave, we begin to ask what gives rise to them in the first place. What underlying structure could produce such strange, consistent, and mathematically precise patterns? The answer, as it begins to emerge, lies not in particles alone, but in something more continuous, more pervasive, and quietly present everywhere. As the idea of particles begins to soften, another concept quietly comes into focus. It is not new. In fact, it has been part of physics for quite some time. But its importance becomes much clearer when particles no longer seem like the final layer of reality. This concept is the field. At first, the idea of a field can feel a little abstract, but it begins with something very simple. A field is a quantity that has a value at every point in space. That is the key idea. Not something located in one place, not something confined to a specific object, but something that exists everywhere, continuously. To make this more concrete, it helps to begin with familiar examples. Consider the temperature in a room. At every point in the room, the temperature has a value. It might vary slightly from one place to another, but it is defined everywhere. You could, in principle, assign a number to every location, describing how warm or cool it is. This is a temperature field, or imagine the surface of a calm lake. If you were to measure the height of the water at different points, you would find that it forms a continuous surface. Now, if a small disturbance passes through the water, as waves form and move across that surface, the water itself is always there, but its shape changes over time. This gives a helpful picture. The field is like the water, present everywhere, and what we observe, waves or disturbances, are changes in that field. In physics, one of the earliest and most important examples of a field is the gravitational field. In classical Newtonian physics, gravity is often described as a force acting between two masses. The Earth pulls on an apple, causing it to fall. The Sun pulls on the Earth, guiding its orbit. But this description leaves something slightly unclear. How does the Earth influence the apple without touching it? To address this, physicists introduced the idea of a gravitational field. Instead of thinking of gravity as a direct interaction between objects, we think of the Earth as creating a field that fills the space around it. At every point in space, this field has a value that describes the strength and direction of the gravitational pull. The apple does not need to know about the Earth directly. It responds to the field at its location. This idea shifts the focus. The field becomes the primary object, and the force arises from how other objects interact with that field. A similar idea appears in electromagnetism. In the 19th century, Michael Faraday introduced the concept of electric and magnetic fields. Rather than imagining forces acting across empty space, Faraday visualized fields as real, physical entities that extend outward from charges and currents. Later, James Clerk Maxwell developed a set of equations that describe how these fields behave. Maxwell's equations show that electric and magnetic fields are interconnected and can propagate through space as waves. These waves are what we know as light. This was a remarkable insight. Light is not something that travels through a medium in the way that sound travels through air. It is itself a ripple in the electromagnetic field, and this field is present everywhere. Even in what we might call empty space, the electromagnetic field exists. It may be calm, with no visible disturbances, but it is still there, defined at every point. This brings us to an important distinction. Fields are continuous. Unlike particles, which we tend to imagine as discrete and localized, fields are spread out across space. They do not exist only in certain places. They are not confined to small regions. They form a kind of background structure that is always present. This continuity is essential. It means that a field does not need to move from one place to another in order to have an effect. Instead, changes in the field propagate through space, influencing other systems as they go. For example, when a charged particle accelerates, it creates a disturbance in the electromagnetic field. This disturbance travels outward as an electromagnetic wave, carrying energy and information. That wave can travel vast distances, crossing empty regions of space until it interacts with another particle or detector. In this way, fields provide a natural way to describe how influence spreads. They replace the idea of action at a distance with a more local picture. Instead of objects affecting each other instantly across space, just interactions occur through fields that connect different regions. This idea becomes even more powerful when we consider that multiple fields can exist simultaneously. At any given point in space, there may be a gravitational field, an electromagnetic field, and potentially others, all overlapping and interacting. Each field contributes its own properties, and together they shape the behavior of matter and energy. The world, in this view, begins to look less like a collection of objects and more like a layered system of interacting fields, and this shift has a subtle but important consequence. If fields exist everywhere, then what we call empty space is not truly empty. Even in a region where there are no particles, the fields are still present. They may be in a quiet or unexcited state, but they are not absent. This idea begins to blur the distinction between something and nothing. Empty space is no longer a void. It is a place where fields exist in their lowest energy configuration, ready to be disturbed. And when a disturbance does occur, it appears to us as something we can detect, a particle. This connection between fields and particles is where the story becomes especially interesting. If a field is present everywhere, and if disturbances in that field can move and interact, then it becomes natural to ask whether what we call particles are simply localized disturbances in fields, like small ripples moving across a vast invisible surface. At first, this might sound like a metaphor, but as physics developed further, this idea became more precise. In classical field theory, fields are continuous and smooth. Now, they can vary in strength and direction, and they can support waves and disturbances, but they do not by themselves explain the discrete nature of quantum phenomena, the fact that energy appears in specific amounts and that particles are detected as individual events. To account for this, the concept of the field itself must be extended. It must incorporate the principles of quantum mechanics. This leads to the idea of a quantum field. A quantum field retains the continuity of classical fields, existing at every point in space, but it also incorporates quantization. Disturbances in the field do not occur in arbitrary amounts, but in discrete units. These units correspond to what we observe as particles. So rather than thinking of particles as fundamental objects, we begin to think of them as excitations of underlying fields. The field is always present. The particle is a temporary localized expression of that field. This perspective brings together several threads. The wave-like behavior of particles, the quantization of energy, and the continuous nature of fields all fit naturally within this framework. And perhaps most importantly, it offers a way to move beyond the limitations of the particle picture. Instead of trying to force quantum phenomena into classical categories, we allow for a different kind of foundation, one in which reality is not built from tiny solid pieces, but from something more subtle, something that exists everywhere, even in stillness, something that can give rise to both waves and particles depending on how it is observed. And as this idea settles in, the familiar notion of empty space begins to change once again. It is no longer a passive backdrop. It becomes an active, structured presence, quiet, continuous, and always there. If we take the idea of a field seriously, something that exists everywhere, quietly present even in the absence of anything we would normally call matter, then the next step is to ask how this picture changes when we bring quantum physics into it. Because classical fields, like the electromagnetic field described by James Clerk Maxwell, are smooth and continuous. They can vary in strength, they can ripple, and they can carry energy across space. But they do not, on their own, explain why energy appears in discrete packets, or why particles are detected as individual events. To capture those features, the field itself must obey the rules of quantum mechanics. This leads to what is known as quantum field theory, a framework developed gradually throughout the 20th century by physicists such as Paul Dirac, Werner Heisenberg, and later Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Within this framework, the basic entities are not particles, they are quantum fields. A quantum field can be understood as something that assigns a value to every point in space and time, just like a classical field, but with an important difference. The values of a quantum field are not fixed in a deterministic way. Instead, they are governed by quantum rules, meaning they are subject to uncertainty, superposition, and quantization. This may sound abstract, so it helps to build the idea carefully. Imagine space itself, not as empty, but as filled with various fields. There's an electron field, a photon field, a quark field, and many others. Yet each type of particle that we observe corresponds to its own underlying field. This is a central principle. Every particle is associated with a field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. This means that the electron field exists everywhere, even in regions where no electrons are present. The same is true for all other fields. They are not created when a particle appears, and they do not disappear when a particle is gone. They are always there. In this sense, fields are not things within space. They are properties of space itself. This is a subtle but important shift. In classical thinking, space is a passive stage, an empty arena in which objects exist and move. But in quantum field theory, your space is inseparable from the fields that fill it. To speak of space is, in a very real sense, to speak of these fields. They define what space can do. They determine how energy can appear, how forces can arise, and how interactions take place. At every point in space, each field has a value. But unlike classical fields, these values are not fixed numbers. They are described by operators in a mathematical framework, which encode the possible outcomes of measurements. What we observe depends on how we interact with the field. This brings us to the quantum aspect. In quantum mechanics, systems can exist in superpositions of states. A quantum field inherits this property. It does not have a single, definite configuration at all times. Instead, it exists in a combination of possible configurations, each with a certain probability. When we measure the field, we do not reveal a pre-existing definite value. We obtain one outcome from a range of possibilities, with probabilities determined by the underlying quantum state. This behavior is not limited to isolated particles. It is built into the field itself. The field can fluctuate, even in what we would call empty space. These fluctuations are not caused by external disturbances. They arise naturally from the uncertainty principle. Even in its lowest energy state, often referred to as the vacuum state, a quantum field is not completely still. It exhibits small, unavoidable fluctuations, reflecting the fact that its energy and configuration cannot both be precisely defined. This is sometimes described as vacuum energy. It is a reminder that what appears to be empty space is, in fact, a dynamic and active structure. To make this more concrete, consider the electromagnetic field again. In classical physics, this field can support waves, which we observe as light. In quantum field theory, these waves are quantized. Instead of continuous energy, the field exchanges energy in discrete amounts. Each unit of excitation corresponds to a photon. So when we detect a photon, we're not observing a tiny object traveling through space in the classical sense. We're observing a localized interaction with the electromagnetic field. The photon is the field in motion. This idea applies more broadly. All particles can be understood as excitations of their respective fields. They're not independent entities moving through empty space, but manifestations of underlying fields that extend everywhere, whereas this helps explain several features of particles that would otherwise seem puzzling. For example, all electrons are identical. No matter where or when they are observed, they have the same mass, the same charge, and the same intrinsic properties. In a particle-based view, this might seem like an unlikely coincidence. Why should every electron be exactly the same? But in a field-based view, the explanation is natural. All electrons are excitations of the same electron field. They are not separate objects with independent identities. They're different expressions of the same underlying structure. It is similar to how every wave on the surface of a lake follows the same physical rules, because all waves arise from the same body of water. Another important feature is that fields can interact with one another. The electron field interacts with the electromagnetic field, allowing electrons to emit and absorb photons. Quark fields interact through the strong nuclear force, mediated by gluon fields. These interactions are described by precise mathematical rules, known as interaction terms in the equations of quantum field theory. These rules allow physicists to calculate probabilities for various processes, such as scattering events, particle decays, and energy transfers. And remarkably, these calculations match experimental results with extraordinary accuracy. One of the most precise agreements between theory and experiment comes from quantum electrodynamics, the quantum field theory of the electromagnetic field and its interaction with charged particles. The predicted value of the electron's magnetic moment, and calculated using quantum electrodynamics, matches experimental measurements to more than 10 decimal places. This level of precision is almost difficult to comprehend. It suggests that the underlying framework is not only conceptually sound, but also deeply aligned with the structure of reality. And yet, despite this success, the picture it presents is quite different from the one we began with. We started with the idea of solid objects, composed of smaller solid pieces. We moved to atoms, then to subatomic particles, and now to fields. At each step, the notion of solidity has faded, replaced by something more abstract. Fields do not have sharp edges. They do not occupy a single location. They're not made of smaller parts in the usual sense. They're continuous, pervasive, and governed by probabilistic rules. And what we call particles, those discrete detectable events, emerge from these fields when they are excited in specific ways. This leads to a quiet but profound shift in perspective. Instead of asking how particles move through space, we begin to ask how fields behave, how they fluctuate, and how their excitations give rise to the phenomena we observe. Particles become secondary. They are no longer the fundamental building blocks, but rather the visible traces of something deeper, something that is always present, even in stillness, something that does not appear only when we look for it, but exists continuously, shaping the structure of reality at every point. And as this idea settles in, the distinction between space and substance begins to blur. Space is not empty. It is filled with fields, and those fields, quietly and persistently, form the foundation of everything we experience. If fields are present everywhere, quietly filling space, then the next question naturally arises. What exactly are we observing when we detect a particle? One of the most helpful ways to approach this is through analogy, not because the analogy is perfect, but because it gently guides intuition in the right direction. Imagine a perfectly still lake. The water is calm, flat and continuous. It extends across the entire surface with no obvious structure or features. Now imagine dropping a small pebble into that lake. At the point of impact, a disturbance appears. Ripples begin to spread outward, forming circular waves that move across the surface. The ripples are not separate objects sitting on top of the water. They are patterns within the water itself. If you were to watch carefully, you would not see the ripple as something independent from the lake. You would see the lake behaving in a particular way at a particular place and time. This is a useful way to think about what physicists call an excitation. An excitation is a disturbance in a field. The field is always there, just as the water is always there. But when energy is added in a specific way, the field responds. It vibrates, oscillates, or forms a localized pattern that can move through space. And that localized pattern is what we observe as a particle. In quantum field theory, this idea is made precise. Each type of particle corresponds to a specific field. The electron field gives rise to electrons. The electromagnetic field gives rise to photons. The quark fields give rise to quarks. And when the field is in its lowest energy state, nothing is observed. There are no particles present. But when the field is excited, when energy is introduced in discrete amounts, it produces a localized disturbance. That disturbance behaves in many ways like what we traditionally call a particle. It can carry energy and momentum. It can interact with other excitations. It can be detected at a specific location when measured. But it is not an object in the classical sense. It is a process. It is something happening within the field, rather than something existing independently of it. This shift from objects to processes is subtle, but it changes the way we think about reality. Instead of imagining tiny solid entities moving through empty space, we begin to imagine continuous fields within which localized patterns form, evolve, and dissolve. The particle is the pattern. The field is the underlying reality. This perspective also helps explain one of the most striking features of quantum particles. They're perfectly identical. Every electron in the universe has exactly the same mass, exactly the same charge, and exactly the same intrinsic properties. There is no variation, no slight differences, no individuality in the classical sense. If electrons were tiny, independent objects, this uniformity would be quite surprising. It would suggest that every electron was somehow manufactured to identical specifications. But in a field-based view, the explanation becomes much simpler. All electrons are excitations of the same electron field. They are not separate entities with their own identities. And they are different instances of the same underlying structure behaving in the same way. It is similar to how every ripple on a lake follows the same physical rules, because all ripples arise from the same body of water. This also explains why particles can be created and destroyed. In classical thinking, objects persist. They may change form, but they do not simply appear or vanish without cause. In quantum field theory, what we call particle creation and annihilation are natural processes. When enough energy is concentrated in a field, an excitation can form. When that excitation loses energy, or interacts with another excitation, it can disappear. The field remains, only the pattern changes. This is observed in high-energy experiments such as those conducted at particle accelerators, like the Large Hadron Collider at CERN. When particles collide at high energies, new particles can be created from the energy of the collision. This is consistent with the principle that energy and mass are related, expressed by Einstein's famous relation, energy equals mass multiplied by the speed of light squared. In this context, energy is transferred into the field, producing new excitations that we detect as particles, and when these excitations interact or decay, the energy is redistributed, often producing different particles. So what we observe in these experiments are not tiny objects bouncing off one another, but rather interactions between excitations of underlying fields. This view also helps clarify why particles exhibit both wave-like and particle-like behavior. As excitations of a field, they naturally inherit wave-like properties. They can spread out so as to interfere and exist in superpositions. At the same time, when they interact with the detector, they produce localized events, which appear particle-like. The duality is not a contradiction. It is a reflection of the underlying structure. The field supports wave-like behavior, and the excitations of that field can be detected as discrete events. This brings us back to the idea of measurement. When we detect a particle, we are not capturing a tiny object in isolation. We are observing a specific interaction between a field excitation and a measuring device. The outcome is localized, but the underlying process is not. The excitation itself may be spread out across space, described by a wave function that encodes probabilities. Only when it interacts with the detector does it produce a definite outcome. And this is why particles can appear to behave differently depending on the experimental setup. In the double-slit experiment, the excitation of the electron field evolves in a way that allows for interference. When measured differently, the same excitation produces a different pattern of outcomes. The behavior is not determined by the particle alone, but by the structure of the field and the nature of the interaction. As this picture becomes clearer, the language we use begins to shift. The word particle remains useful, but it is no longer taken to mean a tiny, solid object. It becomes a convenient label for a particular kind of excitation, a way of describing how a field behaves under certain conditions, and this leads to a deeper understanding of what is truly fundamental. The field is primary. It exists everywhere, continuously, whether or not any excitations are present. The particle is secondary. It is a temporary, localized expression of the field, appearing when energy is introduced in a specific way. This perspective also suggests that what we perceive as stable objects, tables, walls, and even our own bodies, are, at a deeper level, composed of countless interacting excitations across many different fields. These excitations form patterns that are stable over time, giving rise to the appearance of solid, persistent objects. But beneath that stability there is constant activity, fields interacting, fluctuating, and exchanging energy in subtle ways. The solidity we experience is not a reflection of static substance, but of dynamic processes held in balance. And as this idea settles in, the picture of reality becomes both simpler and more profound. Instead of a universe built from tiny pieces, we begin to see a universe built from continuous structures. Instead of objects moving through empty space, we see patterns moving through fields. Instead of things, we find processes, quiet, consistent, and unfolding everywhere at once. If each type of particle arises from its own field, then the universe is not built from a single, unified substance, but from many different fields existing together. At every point in space, there is not just one field quietly present, but a whole collection of them. The electron field is there, the electromagnetic field is there, various quark fields are there, neutrino fields, gluon fields, and others all coexist, overlapping in the same regions of space. This may sound crowded, but it does not lead to confusion. Fields are not objects that take up space in the way physical things do. They're more like layers of properties, each defined at every point, each capable of varying independently, yet able to influence one another. It is similar, in a very loose sense, to how multiple musical notes can exist at the same time in a piece of music. Each note has its own frequency, its own character, but they can combine to form a richer structure. The notes do not compete for space. They coexist, interacting through harmony. In the same way, the fields that make up the universe form a kind of layered structure. Each field has its own identity, its own rules, and its own possible excitations. And yet they do not exist in isolation. They interact. To understand this collection of fields in a more organized way, physicists developed what is known as the Standard Model of particle physics. This is not a model in the sense of a simple diagram or analogy. It is a detailed mathematical framework that describes the fundamental fields known to exist and the ways in which they interact. The Standard Model includes several categories of fields. First, there are the fermion fields, which give rise to what we often think of as matter particles. These include the electron field, the up quark field, the down quark field, and others. These fields produce particles that make up atoms and, by extension, the structures we encounter in everyday life. Then there are the gauge fields, which are associated with forces. The electromagnetic field, for example, gives rise to photons. The strong nuclear field gives rise to gluons. The weak nuclear field gives rise to particles known as W and Z bosons. Each of these fields plays a specific role. Fermion fields provide the building blocks of matter. Gauge fields mediate interactions between those building blocks. And then there is a third type of field, the Higgs field, which plays a unique role in giving particles mass through its interactions with other fields. Together, these fields form a kind of underlying architecture for the universe, and this architecture has been tested extensively. Experiments conducted at large research facilities, such as the Large Hadron Collider at the European Organization for Nuclear Research, have confirmed many of the predictions of the Standard Model with remarkable accuracy. The discovery of the Higgs boson in 2012 provided strong evidence for the existence of the Higgs field, completing a key part of the framework. Despite its complexity, the Standard Model reveals something quite elegant. The diversity of particles we observe does not arise from a large number of unrelated entities, but from a relatively small set of fields, each capable of producing specific kinds of excitations. In this sense, the richness of the physical world emerges from a limited set of underlying ingredients. But the true power of this framework lies not just in identifying fields, but in describing how they interact. Fields do not simply coexist without influence. They are coupled to one another in precise ways, meaning that the state of one field can affect the behavior of another. For example, the electron field interacts with the electromagnetic field. This interaction allows electrons to emit and absorb photons. It is the basis for phenomena such as light emission, electrical currents, and chemical bonding. Similarly, quark fields interact with the strong nuclear field. This interaction binds quarks together to form protons and neutrons, which in turn form atomic nuclei. These interactions are not arbitrary. They are governed by specific mathematical rules encoded in the equations of quantum field theory. These rules determine how likely different processes are, such as scattering events, particle decays, and energy exchanges. To make predictions, physicists often calculate probabilities for different outcomes. For instance, when two particles collide at high energy, there may be several possible results. The equations of the Standard Model allow physicists to calculate the probability of each outcome with remarkable precision. These calculations are then tested in experiments. Detectors at facilities like CERN record the results of millions or even billions of particle collisions, and the observed patterns are compared with theoretical predictions. The agreement is often astonishingly close. This consistency suggests that the interactions between fields are not only well described by the theory, but deeply embedded in the structure of reality. And yet the picture that emerges is quite different from the one we began with. We no longer see a world composed of independent objects moving through empty space. Instead, we see a network of interacting fields, each present everywhere, each capable of influencing the others. Particles, raw in this view, are not isolated entities. They are points where fields interact in particular ways. When an electron emits a photon, it is not a tiny object throwing off another tiny object. It is change in the state of the electron field coupled with a change in the electromagnetic field. The process is continuous at the level of fields, even if the outcome appears discrete. This perspective also helps explain why forces exist. In classical physics, forces are often treated as fundamental. Gravity pulls objects together. Electric charges attract or repel. These forces are described in terms of interactions between objects, but in a field-based view, forces emerge from interactions between fields. The electromagnetic force, for example, arises from the interaction between charged particle fields and the electromagnetic field. The strong force arises from interactions involving quark fields and gluon fields. These forces are not separate entities acting at a distance. They are expressions of how fields influence one another. This brings us to a subtle but important shift in understanding. Instead of asking why objects exert forces on each other, we begin to ask how fields are coupled and how changes in one field propagate through others. The focus moves from objects to relationships, from isolated entities to interconnected systems. And this interconnectedness is present everywhere. At every point in space, multiple fields overlap, interact, and evolve together. Even in regions where no particles are detected, the fields remain, quietly influencing the structure of reality. The universe, in this sense, is not a collection of separate pieces. It is a continuous dynamic system of interacting fields, and what we observe, particles, forces, and interactions, are the visible expressions of this deeper structure. As this picture becomes clearer, the idea of a force begins to feel less like a separate ingredient and more like a consequence of something more fundamental, something that arises naturally from the way fields behave. And this invites the next step in understanding. If fields are the foundation, and if their interactions give rise to everything we observe, then perhaps what we call forces are not fundamental at all, but emergent features of a deeper, field-based reality. When we press our hand against a table, feel the pull of gravity, or notice the faint warmth of sunlight on our skin, it is natural to describe these experiences in terms of forces. We say the table pushes back against our hand. We say the earth pulls objects downward. We say light carries energy across space. These descriptions are useful, and they capture something real about how the world behaves. But within the framework of quantum field theory, the idea of a force begins to take on a different meaning. Rather than being a fundamental ingredient of nature, a force becomes something that emerges from interactions between fields. To understand this, it helps to revisit a familiar example. Consider two electrons. In classical physics, we would say that each electron carries a negative electric charge and that they repel each other through the electromagnetic force. This force acts across space, pushing the electrons apart. But in a field-based description, we look more closely at what is happening beneath this interaction. Each electron is an excitation of the electron field. At the same time, there is an electromagnetic field present everywhere in space. The electron field and the electromagnetic field are not independent. They are coupled, meaning that changes in one field can influence the other. When an electron is present, it modifies the electromagnetic field in its vicinity. This modification spreads outward through space as a change in the field's configuration. If another electron is nearby, it responds to the altered electromagnetic field at its location. The interaction between the two electrons is not a direct push or pull between objects. It is a mediated process carried by the electromagnetic field, and this mediation can be described more precisely. In quantum field theory, interactions between charged particles are often represented in terms of the exchange of photons. A photon is the quantum of the electromagnetic field, the smallest possible excitation of that field. When two electrons interact, the process can be understood as involving the emission and absorption of photons. One electron emits a photon into the electromagnetic field, and another electron absorbs it. This exchange transfers energy and momentum between the electrons. It is important to be careful with this picture. The photons involved in these interactions are often referred to as virtual photons. They are not directly observed as particles of light travelling freely through space. Instead, they are part of the mathematical description of how the fields interact. They represent the way in which the electromagnetic field mediates the interaction between charged excitations. This framework is known as quantum electrodynamics, often abbreviated as QED, developed by physicists such as Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the mid-20th century. Quantum electrodynamics provides a detailed and highly accurate description of how charged particles interact through the electromagnetic field. It is one of the most successful theories in all of science. To give a sense of its precision, consider the magnetic moment of the electron, a property that describes how the electron responds to magnetic fields. Quantum electrodynamics predicts the value of this property with extraordinary accuracy. The agreement between theory and experiment extends to more than 10 decimal places, where this level of precision suggests that the underlying description is not merely approximate, but deeply aligned with the structure of reality. And yet, the conceptual picture it provides is quite different from the classical one. Instead of imagining forces acting directly between objects, we imagine fields interacting with one another, with these interactions giving rise to observable effects. This idea extends beyond electromagnetism. The strong nuclear force, which binds quarks together inside protons and neutrons, arises from interactions involving the strong nuclear field. The excitations of this field are known as gluons, which mediate the interactions between quarks. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by particles known as W and Z bosons, which arise from the weak field. Each of these forces can be understood as a specific pattern of interaction between fields, governed by precise mathematical rules. What we perceive as a force is the result of these interactions unfolding over time. To bring this back to everyday experience, consider once again the sensation of touching a surface. When your hand presses against a table, the atoms in your hand do not come into direct contact with the atoms in the table. Instead, the electrons in your hand interact with the electrons in the table through the electromagnetic field. The repulsion you feel is the result of these interactions. At a deeper level, it is the exchange of energy and momentum between excitations of the electron field mediated by the electromagnetic field. This process happens continuously and seamlessly, giving rise to the stable, the solid sensation we experience. Similarly, when you see an object, what you're detecting are photons, excitations of the electromagnetic field interacting with the electrons in your eyes. These interactions trigger signals that are processed by the brain, creating the experience of sight. Even something as simple as the warmth of sunlight involves countless interactions between fields, with photons transferring energy to matter through well-defined processes. In this way, the abstract framework of quantum field theory connects directly to everyday phenomena. The forces we experience are not separate from the underlying structure of reality. They are expressions of how fields behave and interact. This perspective also helps clarify why forces have specific strengths and ranges. For example, the electromagnetic force can act over long distances because the photon is massless. This allows disturbances in the electromagnetic field to propagate freely across vast regions of space. In contrast, the weak nuclear force has a very short range, because the particles that mediate it, the W and Z bosons, have large masses. This limits how far the corresponding field interactions can extend. These properties are not arbitrary. They arise naturally from the characteristics of the fields and their excitations, and once again, the focus shifts. Instead of asking why objects attract or repel each other, we ask how fields are structured, how they couple, and how their excitations propagate. The idea of a force becomes less like a fundamental cause and more like a description of what happens when fields interact in specific ways. There is a certain elegance in this. A wide variety of phenomena, electricity, magnetism, nuclear interactions, can all be understood within a unified framework, where fields are primary and interactions between them give rise to everything we observe. And yet, despite this clarity, the picture remains somewhat abstract. We do not directly see fields. We do not perceive their fluctuations or their interactions. What we experience are the outcomes, the forces, the motions, the changes in energy. But beneath those outcomes lies a continuous dynamic interplay of fields, quietly shaping the behavior of the universe at every moment. And as this idea settles in, the notion of a force begins to feel less like something separate and more like a natural consequence of a deeper structure. A structure in which everything is connected through fields, and where interactions rather than objects form the foundation of what we experience. There is a quiet question that naturally arises once we begin to see particles as excitations of fields. If particles are not fundamental objects but patterns within fields, then where do their properties come from? In particular, what gives a particle its mass? Mass in everyday experience feels like a deeply intrinsic property. A rock is heavy, a feather is light. These differences seem to belong to the objects themselves, as though mass is something contained within them. But within the framework of quantum field theory, this intuition begins to shift. Mass is not simply something a particle has. It is something that arises from how a field interacts with another field. Yet, to understand this, we need to introduce one of the most important and subtle components of modern physics: the Higgs field. Unlike many other fields, which can be zero in empty space, the Higgs field has a non-zero value everywhere. Even in what we would normally call a perfect vacuum, the Higgs field is present, quietly filling all of space with a constant background value. This is a defining feature. The Higgs field does not switch off. It does not vanish when no particles are present. It is always there, like an invisible medium permeating the entire universe, and it is through interaction with this field that certain particles acquire mass. The idea was developed in the 1960s by several physicists, including Peter Higgs, François Englert, and Robert Brute. They were trying to solve a problem within the emerging framework of quantum field theory. At the time, the equations describing fundamental interactions suggested that certain particles should be massless, but experiments showed that these particles do in fact have mass. The challenge was to explain how mass could arise without breaking the mathematical consistency of the theory. The solution they proposed was both elegant and surprising. They suggested that space is filled with a field, the Higgs field, and that particles moving through this field interact with it. This interaction gives rise to the property we perceive as mass. To make this more intuitive, imagine moving through a crowded room. If the room is empty, you can walk freely with little resistance. But if the room is filled with people, or your movement becomes more difficult, you are slowed down not because you've changed, but because of your interaction with the environment. In a similar way, a particle moving through the Higgs field experiences a kind of resistance, which manifests as mass. This analogy is not perfect, but it captures the central idea. Mass is not an intrinsic substance. It is an effect of interaction. Different particles interact with the Higgs field in different ways. Some interact strongly and acquire a large mass. Others interact weakly and remain relatively light. Some, like photons, do not interact with the Higgs field at all, and therefore have no mass. This explains why the photon, the excitation of the electromagnetic field, travels at the speed of light, while other particles move more slowly. The presence of mass changes how a particle responds to forces and how it moves through space. In precise terms, mass is related to how much a particle resists changes in its motion. This is sometimes called inertia. In classical physics, this relationship is expressed through Newton's second law, which can be stated as force equals mass multiplied by acceleration. In the context of quantum field theory, this resistance to acceleration emerges from the interaction between a particle's field and the Higgs field. The deeper implication is that mass is not a standalone property. It is relational. It depends on how one field interacts with another. This idea remained theoretical for several decades. The Higgs field itself could not be observed directly. What physicists could look for was evidence of its excitation, a particle associated with the field, known as the Higgs boson. Detecting this particle became one of the major goals of experimental physics. To do so required enormous energies, far beyond what could be achieved in earlier experiments. This led to the construction of the Large Hadron Collider at the European Organization for Nuclear Research, located near Geneva. This machine accelerates protons to extremely high speeds and then collides them, creating conditions similar to those that existed shortly after the beginning of the universe. In these collisions, energy is concentrated in such a way that new particles can be produced, including, potentially, the Higgs boson. after many years of preparation, data collection, and analysis. A significant announcement was made in 2012. Scientists at the Large Hadron Collider reported the discovery of a new particle consistent with the predicted properties of the Higgs boson. This was a landmark moment. It provided strong evidence that the Higgs field is not just a theoretical construct, but a real feature of the universe. The discovery did not directly show the field itself, but it confirmed the existence of its excitation, much like observing a ripple confirms the presence of water. This reinforced a broader theme that has been unfolding. Fields are not abstract mathematical tools alone. They correspond to something physically real, something that can be probed, tested, and observed through their effects. The Higgs field in particular highlights how deeply this idea runs, or it suggests that one of the most fundamental properties we associate with matter, mass, does not originate from the particles themselves, but from their interaction with a field that exists everywhere. This has a quiet but profound implication. If mass arises from interaction, then what we perceive as the substance of matter is not a fixed, intrinsic quality. It is the result of relationships. The electron is not inherently massive in isolation. Its mass emerges because of how the electron field interacts with the Higgs field. The same is true for many other particles. This shifts our understanding in a subtle way. Instead of thinking of properties as belonging to objects, we begin to think of them as emerging from interactions between fields. The universe, in this view, is not built from isolated pieces with predefined characteristics. It is built from a network of fields, each influencing the others, each contributing to the properties we observe. And once again, the idea of a particle as a self-contained entity becomes less central. What matters is the field and the way it behaves. What matters is the interaction and the patterns it produces. Mass, solidity, and stability all emerge from these deeper processes, and beneath it all, quietly present at every point in space, the Higgs field continues to exist, shaping the behavior of particles in a way that is both subtle and essential. It does not announce itself. It does not move or ripple in obvious ways, but without it, the structure of the universe would be entirely different. Atoms would not form as they do. Matter would not have the properties we rely on. The world as we experience it would not exist in the same way. And so, what seems like a simple question, why do things have mass, leads us back once again to the same underlying idea. That reality is not made of things alone, but of fields and the interactions between them. When we imagine empty space, it is natural to picture something still and quiet. A perfect vacuum in everyday thinking is a place where nothing exists. No particles, no light, no motion. Just an absence of everything. But within quantum field theory, this picture begins to change in a very gentle, yet profound way. Because even when all particles are removed, the fields remain, and those fields are never completely still. At the heart of this idea is something known as vacuum fluctuations. To understand this, we return briefly to the uncertainty principle, introduced by Werner Heisenberg. It tells us that certain pairs of physical quantities, such as energy and time, cannot both be precisely defined at the same moment. In simple terms, this means that the energy of a system cannot remain perfectly fixed over very short intervals of time. There is always a small amount of uncertainty. This uncertainty has consequences. Even in the lowest possible energy state, what we call the vacuum state, a quantum field cannot be completely motionless. It must exhibit tiny fluctuations, brief variations in energy that arise naturally from the rules of quantum mechanics. These fluctuations are not caused by anything external. They are not disturbances entering from outside. They are intrinsic to the field itself. This means that empty space is not truly empty. It is filled with fields that are constantly subtly fluctuating. These fluctuations are often described as zero-point energy. The term zero point refers to the lowest possible energy state of a system. Even at this lowest level, the energy does not drop to zero. There is always a small, irreducible amount of energy present. This is not just a theoretical idea. There are experiments that provide evidence for it. One of the most well-known is the Casimir effect, predicted by Hendrik Casimir in 1948. In this experiment, two very thin metal plates are placed extremely close together in a vacuum. At distances on the order of a few nanometers, which is about a few billionths of a meter, an attractive force appears between the plates. This force cannot be explained by classical physics. Instead, it arises because the presence of the plates alters the allowed modes of the electromagnetic field between them. Fewer fluctuations can exist in the space between the plates than outside, creating a pressure difference that pushes the plates together. It is a subtle effect, but it has been measured with high precision, and it provides direct evidence that even in a vacuum, fields are active. Another way to think about vacuum fluctuations is through the idea of virtual particles. This concept can be a little misleading if taken too literally, so it helps to approach it carefully. Virtual particles are not particles in the usual sense. They are not objects that can be directly observed or detected. Instead, they are a way of describing temporary fluctuations in a field. In quantum field theory, interactions between fields can be represented mathematically as exchanges of energy. In certain calculations, these exchanges are described as particles appearing briefly and then disappearing. These are called virtual particles. They do not exist in the same way as real particles, which can be detected and measured. But they play a crucial role in the behavior of fields. For example, the interaction between two charged particles can be described as involving the exchange of virtual photons. These photons are not directly observed, but their effects are measurable. They contribute to forces, influence energy levels, and affect how particles behave. In this sense, the vacuum is not a static background. It is a dynamic environment filled with activity at a very small scale, at even smaller scales, and this activity becomes more complex. Some physicists describe the vacuum as having a kind of structure known as quantum foam. This idea was introduced by John Wheeler in the 1950s. At extremely small distances on the order of the Planck length, which is about 1 divided by 10 followed by 35 zeros of a meter, the smooth picture of space begins to break down. Quantum fluctuations in both fields and space-time itself may become so large that the geometry of space is no longer stable. Instead of a smooth, continuous structure, space may resemble a constantly changing, foamy landscape. This is still a speculative idea, as we do not yet have a complete theory of quantum gravity that fully describes these scales. But it points toward a deeper possibility, that even the fabric of space itself is not fixed but dynamic, i.e. that what we think of as emptiness is in fact a rich and active domain. Returning to more familiar scales, the idea that the vacuum is not empty has practical consequences. For instance, vacuum fluctuations can influence the behavior of atoms. They contribute to small shifts in energy levels known as the Lamb shift, first measured by Willis Lamb in 1947. These shifts are tiny, but they can be detected with precise measurements, and they match the predictions of quantum field theory. Once again, the theory aligns with observation, and once again the underlying picture becomes more intricate. Empty space is no longer a simple absence. It is a state of lowest energy, but not zero energy. It is a state where fields are present, fluctuating, and capable of giving rise to observable effects. But this leads to a subtle but important shift in perspective. If the vacuum itself contains energy, then it plays an active role in the behavior of the universe. It is not just a backdrop against which events occur, it is part of the system. In cosmology, this idea connects to questions about dark energy, the expansion of the universe, and the large-scale structure of space-time. While these topics extend beyond our immediate focus, they reflect the broader significance of the vacuum. The concept of nothing becomes much more nuanced. It is no longer a simple void. It is a state defined by fields, by fluctuations, and by the rules of quantum mechanics. And this invites a deeper reflection. If what we call empty space is filled with activity, if fields are present everywhere, if fluctuations are unavoidable, then the distinction between something and nothing becomes less clear. The vacuum is not the absence of reality. It is a particular configuration of it, a quiet state perhaps, but not an empty one. And as this idea settles in, it prepares the way for an even more subtle question. If even emptiness has structure, activity, and energy, then what does it truly mean for something to exist? If we look closely at the patterns that emerge from fields and their interactions, a quiet theme begins to appear again and again. Beneath the complexity there is order, and one of the most powerful ways physicists understand that order is through the idea of symmetry. In everyday language, symmetry often refers to balance or visual harmony. A shape is symmetrical if it looks the same when reflected or rotated. But in physics, symmetry has a broader and more precise meaning. A symmetry is a transformation that can be applied to a system without changing its fundamental behavior. In other words, if you perform a certain change and the underlying laws remain the same, then the system possesses a symmetry. This might sound abstract, but it has very real consequences. Consider a simple example. If you perform an experiment today and then repeat it tomorrow under the same conditions, you expect the outcome to be the same. The laws of physics do not change from one day to the next. This is a symmetry in time. Similarly, if you perform an experiment in one location and then repeat it somewhere else, the result should not depend on where you are. The laws of physics are the same in New York, Tokyo, or on a distant planet. This is a symmetry in space. These ideas may seem almost obvious, but they carry deep implications. In the early 20th century, a mathematician named Emmy Noether made a remarkable discovery. She showed that every continuous symmetry in the laws of physics corresponds to a conservation law. This connection is known as Noether's theorem. It can be expressed clearly. If a system behaves the same under a shift in time, then energy is conserved. If a system behaves the same under a shift in position, then momentum is conserved. If a system behaves the same under rotation, then angular momentum is conserved. This is not a coincidence. It is a fundamental relationship between the structure of the laws and the quantities that remain constant. Symmetry in this sense is not just a mathematical curiosity. It is a guiding principle that shapes the behavior of the universe. And within quantum field theory, symmetry plays an even more central role. Fields are not arbitrary. Their properties and interactions are constrained by symmetries. For example, the electromagnetic field is governed by a symmetry known as gauge symmetry. This symmetry ensures that certain transformations of the field do not change observable outcomes, and it leads directly to the existence of the photon as the carrier of the electromagnetic interaction. Gauge symmetry is not something we see directly. It is a hidden feature of the equations that describe the field, but its consequences are visible in the behavior of particles and forces. This idea extends to other interactions as well. The strong nuclear force and the weak nuclear force are also described by gauge symmetries, each with its own mathematical structure. These symmetries determine how the corresponding fields behave and how they interact with other fields. In this way, the fields that make up the universe are not just present everywhere. They are organized by underlying symmetries. These symmetries act like rules that constrain what is possible and what is not. They shape the patterns that can emerge. But there is another layer to this story. Not all symmetries are visible in the world we observe. Some symmetries are hidden. This brings us to the idea of symmetry breaking. To understand this, so imagine a perfectly round hill with a ball balanced at its very top. The system is completely symmetrical. There is no preferred direction. The ball could roll down in any direction, and all directions are equally valid. But the moment the ball begins to roll, that symmetry is broken. The system chooses a particular direction, even though the underlying structure remains symmetrical. This is a simple analogy, but it captures the essence of spontaneous symmetry breaking. In physics, a system may have symmetrical laws, but the state it settles into may not reflect that symmetry. This has profound consequences. The Higgs field provides a clear example. The equations that describe the Higgs field are symmetrical, but the lowest energy state of the field is not zero. Instead, the field settles into a non-zero value throughout space, breaking the symmetry. This symmetry breaking is what allows particles to acquire mass. Without it, the properties of particles would be very different. More generally, symmetry breaking helps explain how complexity can arise from simplicity. At a fundamental level, the laws of physics may be governed by relatively simple and symmetrical principles. But as systems evolve, these symmetries can break in specific ways, giving rise to the rich variety of structures we observe. This includes not only particles and forces, but also the formation of atoms, molecules, and larger structures. From a small set of underlying rules, a vast and intricate universe emerges. Fields encode these rules. Their mathematical structure reflects the symmetries of the system, and their behavior reveals how those symmetries are expressed or broken. This perspective offers a different way of understanding complexity. Instead of seeing complexity as something that requires many independent ingredients, we begin to see it as something that can arise from simple principles, applied repeatedly and consistently. A small number of fields governed by a small number of symmetries can produce a wide range of phenomena. There is a quiet elegance in this. The universe does not need an enormous number of separate rules for each phenomenon. Instead, it relies on a coherent framework where symmetry provides structure and consistency. And yet, the outcome is far from simple, because when symmetries are broken, when fields interact, and when fluctuations occur, the resulting patterns can be incredibly rich. This interplay between symmetry and symmetry breaking is one of the key drivers of structure in the universe. It is what allows uniform laws to give rise to diverse outcomes. It is what allows a smooth, continuous field to produce localized excitations. It is what allows a simple set of equations to describe a world filled with complexity. As we reflect on this, the idea of fields becomes even more meaningful. They're not just entities that exist everywhere. They are structured by deep principles. They carry within them the symmetries that define what is possible, and through their interactions and fluctuations, they give rise to everything we observe. The patterns we see in nature, the stability of atoms, the behavior of forces, the formation of matter, are not random. They are expressions of hidden order. An order that is not always visible on the surface, but is encoded in the very fabric of the fields themselves. And as we continue to explore this idea, it becomes increasingly clear that what appears complex may, at its core, be guided by something remarkably simple. As the picture of reality shifts from particles to fields, another question begins to quietly emerge. If fields are fundamental, then what exactly are they? Are they a kind of substance, spread out across space, like an invisible fluid? Or are they something more abstract, something closer to a pattern, a structure, or even a form of information? This question has led some physicists to explore a different way of thinking about the foundations of reality. One of the most influential voices in this direction was John Archibald Wheeler, who proposed a simple but striking phrase, "it from bit." The idea behind this phrase is that physical reality, the it, may arise from information, the bit. In other words, what we perceive as matter, energy, and space might ultimately be rooted in something more fundamental, the encoding and processing of information. At first, this may seem like a philosophical idea rather than a physical one, but there are reasons grounded in science that make this perspective worth considering. To begin with, quantum theory already places information at the center of how we describe physical systems. The wave function, which represents the state of a quantum system, does not describe a physical object in the classical sense. Instead, it encodes the probabilities of different outcomes. It tells us what we can know and what we can predict about a system. In this sense, the wave function is not a piece of matter. It is a mathematical object that carries information, and when we perform a measurement, we are not simply revealing a pre-existing property. We are interacting with the system in a way that produces a specific outcome from a range of possibilities. This process can be understood as an update in information. What was previously uncertain becomes known. This connection between quantum theory and information becomes even clearer when we consider how quantum systems can be used to store and process information. In classical computing, information is stored in bits, which can take on values of 0 or 1. In quantum computing, the basic unit is the qubit, which can exist in a superposition of states. This allows quantum systems to encode and manipulate information in ways that are not possible with classical systems. The behavior of qubits is governed by the same principles that describe quantum fields and particles. Superposition, entanglement, and uncertainty are not just abstract ideas. They are operational features that can be used to perform calculations, transmit information, and explore new forms of computation. This suggests that information is not just a tool we use to describe physical systems, it is something that is built into the fabric of those systems. From this perspective, fields themselves can be seen as carriers of information. At every point in space, a field has a value, or more precisely, a set of possible values described by its quantum state. These values encode information about the system. When fields interact, they exchange information. When a photon is emitted or absorbed, information is transferred from one part of the system to another. When particles scatter, their interactions can be described in terms of changes in the information encoded in the fields. Even the concept of entropy, which plays a central role in thermodynamics, is deeply connected to information. Entropy can be understood as a measure of uncertainty or disorder, which in turn relates to how much information is needed to describe a system. This connection was explored by physicists such as Claude Shannon, who developed information theory, and later by researchers studying the thermodynamics of information. In this light, the boundary between physical processes and informational processes becomes less clear. They begin to look like different aspects of the same underlying reality. This idea gains further support from certain areas of theoretical physics. For example, the study of black holes has revealed deep connections between gravity, thermodynamics, and information. The work of Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not their volume. This suggests that the information content of a region of space may be encoded on its boundary. While this idea leads into more advanced topics, it reinforces a broader theme. Information is not just something we impose on the world. It may be something the world is made of. Returning to fields, we can begin to ask a different kind of question. Instead of asking what a field is made of, we might ask what information it encodes. Quantum field assigns a set of possible values to every point in space and time. These values evolve according to specific rules, governed by the equations of quantum field theory. In this sense, the field is not a substance. It is a structure, a system that encodes relationships, constraints, and possibilities. The excitations of the field, what we call particles, are then specific patterns within this structure. They're not independent objects, but configurations of information that can be detected and measured. This perspective does not replace the field picture, but it reframes it. Fields are still real, in the sense that they have observable effects and can be described by precise mathematical laws. But their reality may be closer to that of a pattern or a process than that of a material substance. This leads to a subtle shift in how we think about existence. In classical thinking, something exists if it has substance, if it occupies space and persists over time. In an information-based view, something exists if it can be described, if it has structure, if it participates in relationships. Existence becomes less about stuff and more about form. This idea can feel abstract, but it connects back to what we observe. Particles appear as localized events, but their behavior is governed by underlying fields. Fields are continuous, but their behavior is described by mathematical structures that encode information. At every level, the emphasis shifts from objects to patterns, from substance to structure. And as this shift deepens, it invites a more fundamental question. If reality is built from fields, and if fields can be understood as carriers of information, then what is the relationship between information and physical existence? Is information something that describes reality? Or is it something that constitutes reality? This question does not yet have a definitive answer, but it points toward a deeper layer of understanding, one in which the distinction between physics and information theory becomes less clear, and where the foundations of reality may lie not in objects or even fields alone, but in the patterns of information that those fields embody. And as we sit with this idea, it gently opens the door to a new way of thinking, not just about what the universe is made of, but about what it means for anything to be at all. There is a feature of quantum physics that feels, at first, almost like a quiet paradox. It suggests that parts of the universe, even when separated by vast distances, can remain connected in a way that does not fit comfortably within our usual understanding of space. This feature is known as quantum entanglement. To approach it gently, imagine two particles that are created together in a single process. Because they originate from the same interaction, their properties are not independent. Instead, they are described by a shared quantum state. This shared description means that the system must be treated as a whole, not as two separate objects, but as a single, unified entity. For example, consider a pair of particles whose spins are linked. Well, spin is a quantum property that can take on values often described as up or down. If the total spin of the system is constrained in a certain way, then measuring the spin of one particle immediately determines the spin of the other. If one is found to be up, the other must be down. What makes this remarkable is not just the correlation, but the fact that it holds regardless of distance. The two particles can be separated by meters, kilometers, or even light years, and the correlation remains. This was first highlighted in a thought experiment by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. They pointed out that quantum mechanics predicts these kinds of correlations and questioned whether the theory could be complete. Einstein referred to this phenomenon as spooky action at a distance, reflecting his discomfort with the idea that something happening in one location could be immediately connected to something happening far away. At the time, it was not clear whether these correlations reflected a real feature of the world or a limitation of the theory. But in the decades that followed, experiments were designed to test this question. In 1964, John Bell developed a set of inequalities, now known as Bell's inequalities, that could distinguish between classical explanations and quantum predictions. If the correlations between entangled particles could be explained by hidden variables, then certain statistical limits would not be exceeded. But quantum mechanics predicted that these limits could be violated. Beginning in the 1970s and continuing through the work of Alain Aspect in the 1980s, and later Anton Zeilinger and others, experiments were carried out to test these predictions. The results consistently supported quantum mechanics. The correlations between entangled particles exceed what is possible under classical assumptions. This means that the connection between the particles is not simply due to shared initial conditions or hidden properties. It is a deeper kind of relationship. To understand this in the context of fields, it is helpful to shift perspective slightly. If particles are excitations of fields, then entanglement is not a mysterious link between distant objects. It is a property of the underlying fields themselves. When two excitations are created in a single process, the field that gives rise to them is in a particular state, one that encodes correlations across space. The excitations may appear as separate particles, but they are part of a single, extended configuration of the field. In this sense, the entanglement is not something that travels between particles. It is already present in the field. The field does not recognize the same boundaries that we do. From our perspective, the particles are separated by distance. But from the perspective of the field, they are part of a continuous structure. This helps explain why the correlations appear to be instantaneous. There is no signal being sent from one particle to the other. There is no exchange of information that travels faster than light. Instead, the outcomes are correlated because they arise from a shared underlying state. This distinction is important. Entanglement does not allow for faster-than-light communication. It does not enable one observer to send a message to another instantaneously. The outcomes of individual measurements remain random. but the correlations between outcomes are stronger than anything allowed by classical physics. This challenges our intuitive understanding of locality. In classical physics, locality means that objects are influenced only by their immediate surroundings. Interactions occur through direct contact or through fields that propagate at finite speeds. Entanglement suggests that this picture is incomplete. While interactions still respect the speed of light, the structure of the quantum state itself is not confined in the same way. The state can extend across space, linking distant regions into a single system. This leads to a subtle but profound shift. Space, as we experience it, may not be the deepest level of organization. The connections defined by quantum states may be more fundamental than the distances we measure. In some approaches to theoretical physics, this idea is taken even further. Researchers have explored the possibility that space-time itself might emerge from patterns of entanglement. In this view, the geometry of space, its shape, its curvature, its distances, could be a reflection of how quantum systems are entangled. While this remains an area of active research, it highlights a broader theme. The structure of reality may be defined not just by what exists, but by how things are connected. Entanglement reveals that these connections can be deeper and more subtle than classical intuition would suggest. Returning to a more familiar scale, entanglement is not just a theoretical curiosity. It has practical applications. Quantum communication, quantum cryptography, and quantum computing all rely on the properties of entangled systems. These technologies make use of the correlations between quantum states to perform tasks that would be impossible using classical systems alone. For example, quantum key distribution allows two parties to share a secure encryption key, with any attempt at eavesdropping immediately detectable due to the disturbance it introduces in the entangled system. These applications demonstrate that entanglement is not just a philosophical puzzle. It is a real and measurable feature of the world, and yet it continues to challenge our understanding. If two regions of space can be linked in this way, then the idea of complete independence between distant objects becomes difficult to maintain. The universe begins to appear less like a collection of separate parts, and more like an interconnected whole. Fields extend across space, and their states can encode relationships that do not diminish with distance. Particles, as excitations of these fields, inherit these relationships. They are not isolated. They are connected through the underlying structure of the field. As this idea settles in, it invites a different way of thinking about reality. Instead of focusing only on individual entities, we begin to pay attention to the relationships between them. Instead of asking where something is, we ask how it is connected. And in doing so, the picture of the universe becomes less about separation and more about unity, and not in a vague or abstract sense, but in a precise, measurable, and deeply physical way. A way that suggests that what appears distant may, at a deeper level, still be part of the same continuous fabric. Up to this point, space has quietly remained in the background. Even as particles gave way to fields, and even as fields became more abstract and relational, space itself has still felt like a kind of stage, a place where everything happens, a continuous arena in which fields exist, interact, and evolve. But there is a growing idea in modern physics that even this stage may not be fundamental. That space itself, and time along with it, may emerge from something deeper. To begin exploring this, it helps to recall how space is treated in classical physics. In the framework developed by Isaac Newton, space is absolute. It exists independently of the objects within it. It provides a fixed backdrop with well-defined distances and directions. Time, in this view, flows uniformly, the same everywhere. Later, in the early 20th century, Albert Einstein introduced a different picture through the theory of general relativity. In this framework, space and time are combined into a single entity known as space-time. And rather than being fixed, space-time is dynamic. It can curve and stretch in response to the presence of mass and energy. This relationship can be summarized in a simple way. Mass and energy tell space-time how to curve, and space-time tells matter how to move. This description has been confirmed by many observations, from the bending of light around massive objects to the detection of gravitational waves. And yet, there is a tension, and general relativity describes space-time as smooth and continuous. Quantum field theory, on the other hand, describes the behavior of fields using principles that involve uncertainty, discreteness, and fluctuations. When physicists attempt to combine these two frameworks into a single unified theory, often referred to as quantum gravity, they encounter significant challenges. This has led to a deeper question. What if space-time itself is not fundamental? What if it is not the starting point, but the result of something more basic? One approach to this question is known as relational physics. In relational interpretations, space is not something that exists independently. Instead, it is defined by relationships between physical systems. Carlo Rovelli, one of the leading researchers in this area, has argued that the properties of a system are meaningful only in relation to other systems. There is no absolute position, no absolute state, only relationships. In this view, space is not a container. It is a network of relationships. Distance, for example, is not a fixed background property. It emerges from how systems interact with one another. If two systems influence each other strongly, they can be considered close. If their interaction is weak or negligible, they can be considered far apart. This idea may feel unfamiliar, but it aligns with certain features of quantum theory. As we've seen, entanglement can link systems across what appears to be large distances. The strength of their connection is not determined solely by their separation in space. This suggests that spatial distance may not be the most fundamental measure of closeness. Instead, the structure of connections, how systems are related, may play a more central role. Another line of research explores how space-time geometry might emerge from patterns of quantum entanglement. In certain theoretical models, the curvature of space-time is related to the way quantum systems are entangled. Regions that are highly entangled may correspond to regions that are close together in space, while regions with weaker entanglement may appear farther apart. This idea is still being developed, but it offers a fascinating possibility: that the geometry of space is not fixed, but arises from deeper quantum relationships. There are also approaches such as loop quantum gravity, which attempt to describe spacetime itself as composed of discrete elements. In this framework, space is not continuous down to arbitrarily small scales. Instead, it has a granular structure, with smallest units of area and volume. These units are not embedded in a pre-existing space. They are the space. The geometry of space-time emerges from how these discrete elements are connected and arranged. This is quite different from the smooth picture provided by general relativity, but it offers a way to reconcile the principles of quantum mechanics with the nature of space. Across these different approaches, a common theme begins to appear. Space-time may not be the foundation of reality. It may be an emergent structure, something that arises from more fundamental entities such as quantum fields, information, or networks of relationships. This shift has significant implications. If space is emergent, then distance, location, and even the notion of here and there may not be fundamental features of the universe. They may be approximations that hold at larger scales, much like the concept of a solid object emerges from the interactions of atoms. At very small scales, or under extreme conditions, the familiar picture of space-time may break down. This idea also connects to earlier discussions about the vacuum. If fields exist everywhere, and if their fluctuations are unavoidable, then the structure of space is already more complex than it appears. Adding quantum effects to space-time itself suggests that even the geometry of space may fluctuate. At extremely small scales, space may not be smooth at all. It may be dynamic, irregular, and constantly changing. This brings us to a deeper reflection. If both particles and space-time are not fundamental, then what is? Fields provide one layer of description. Information provides another. Relationships between systems offer yet another perspective. Each of these approaches points toward a reality that is less about fixed entities and more about patterns, interactions, and structures that emerge from deeper rules. And as this idea settles in, it begins to prepare the way for an even more unusual possibility. If space itself can emerge from something more fundamental, then perhaps the structure of the universe can be described in ways that do not rely on space in the usual sense at all. Perhaps the geometry we experience is not the starting point, but a kind of projection, a way in which deeper information or relationships are expressed at a scale we can perceive. This leads naturally toward one of the most intriguing ideas in modern theoretical physics, the possibility that the universe, in some sense, may be encoded, that what we experience as a three-dimensional world could arise from information defined on a lower dimensional boundary. A possibility that invites us to rethink not just what reality is made of, but how it is structured at the deepest level. There is an idea in modern physics that feels at first almost like a quiet inversion of everything we have come to expect. It suggests that the world we experience, three-dimensional, extended in space, filled with fields and interactions, may not be the most fundamental description of reality. Instead, it may be something like a projection. This idea is known as the holographic principle. To approach it gently, it helps to begin with something familiar. A hologram is a two-dimensional surface that encodes a three-dimensional image. When light interacts with the surface in the right way, the encoded information produces the appearance of depth. The image seems to occupy space, even though all the information is stored on a flat plane. The holographic principle proposes something similar, but on a much deeper level. It suggests that the information describing a region of space may be fully encoded on its boundary. In other words, everything that happens within a volume of space could, in principle, be described by information located on a lower dimensional surface surrounding that volume. This idea did not arise from simple speculation. It emerged from the study of black holes. In the 1970s, Jacob Bekenstein proposed that black holes have entropy, a measure of the amount of information they contain. Stephen Hawking later showed that black holes emit radiation, now known as Hawking radiation, and therefore have a temperature. What was surprising was how the entropy of a black hole scales. Instead of being proportional to its volume, which might seem intuitive, the entropy is proportional to the area of its event horizon, the surface that marks the boundary of the black hole. This relationship can be expressed clearly. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggests that the information content of the black hole is encoded on its surface. This was a striking result, and it hinted that the fundamental description of a region of space might depend more on its boundary than on its interior. Building on this idea, physicists such as Gerard 't Hooft and Leonard Susskind proposed the holographic principle as a general feature of quantum gravity. They suggested that the physics within a volume of space can be described by a theory defined on its boundary. This idea gained further support through the work of Juan Maldacena in the late 1990s. Maldacena proposed a specific realization of the holographic principle known as the anti-de Sitter and conformal field theory correspondence. This correspondence shows that a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory defined on a lower dimensional boundary. While although the details are mathematically complex, the core idea is surprisingly simple. Two very different descriptions, one involving gravity in a higher dimensional space, and another involving quantum fields on a lower dimensional surface, can describe the same physical reality. This equivalence suggests that the higher dimensional space may not be fundamental. It may emerge from the lower dimensional description. If this idea extends to our own universe, it raises a profound possibility that the three-dimensional space we experience could be a kind of emergent structure, encoded in a deeper, lower dimensional framework. This does not mean that the world is an illusion in the everyday sense. The objects we interact with are real. The forces we feel are real. The fields we have discussed are real in the sense that they have measurable effects and obey consistent laws, but the way these phenomena are organized in space may not be the most fundamental level of description. Instead of being built from the inside out, reality may be defined from the boundary inward. This perspective changes how we think about space itself. In classical physics, space is something that exists independently. It provides the stage on which events unfold. Objects occupy positions within it, and distances are defined by the geometry of the space. In a holographic view, space may be something that emerges from patterns of information. The geometry of space, its shape, its curvature, its distances, could arise from how information is organized and encoded. This connects back to earlier ideas about fields and information. If fields can be understood as carriers of information, and if interactions between fields define the behavior of the universe, then it becomes natural to ask whether the structure of space itself is a reflection of deeper informational relationships. In this view, space is not fundamental. It is a kind of map, a way of organizing information so that it appears as a continuous, extended reality. This idea also helps address certain puzzles in physics. For example, the problem of quantum gravity, how to reconcile the smooth geometry of space-time with the discrete nature of quantum theory, may be approached by recognizing that space-time itself is not fundamental. If space and time emerge from a more basic structure, then the apparent conflict between continuity and discreteness may be resolved at a deeper level. Another implication is that the amount of information that can be stored in a region of space is not determined by its volume, but by its surface area. This places a fundamental limit on the density of information, sometimes referred to as the Bekenstein bound. It suggests that there is a maximum amount of information that can be contained within a given region and that this limit is set by the area of its boundary. This idea has far-reaching consequences for our understanding of black holes, quantum gravity, and the nature of information in the universe. Returning to a more intuitive level, the holographic principle invites us to rethink what we mean by where something is. If the full description of a region can be encoded on its boundary, then the distinction between interior and exterior becomes less absolute. The boundary contains all the information needed to describe the interior. This blurs the line between what is inside and what is outside, and it suggests that spatial relationships may not be as fundamental as they appear. As this idea settles in, it encourages a different way of thinking about reality. Instead of imagining a universe built from objects arranged in space, we begin to imagine a universe defined by patterns of information. Space becomes a way of organizing those patterns. Fields become ways in which information is distributed and evolves. Particles become localized expressions of that information. The familiar picture of a three-dimensional world remains valid at the level of experience. But beneath it, there may be a deeper structure, one in which the geometry of space is not given, but derived. Not fundamental, but emergent. And while this idea is still being explored and refined, it offers a glimpse of a different kind of foundation, one in which reality is not simply extended in space, but encoded, quietly, precisely, and perhaps more simply than it first appears. If we follow the ideas we've been exploring to their natural conclusion, something subtle begins to shift in how we think about the world around us. What we call objects, tables, stones, even our own bodies, start to look less like fundamental things and more like stable patterns within something deeper. At first, this may feel counterintuitive. Mere objects appear solid, persistent, and clearly defined. A chair remains a chair. A mountain remains a mountain. These things seem to exist independently, with their own identity and boundaries. But when we look more closely through the lens of quantum field theory, this apparent solidity begins to soften. A table, for example, is not a single unified object at the most fundamental level. It is a complex arrangement of atoms. Those atoms are themselves composed of nuclei and electrons, and those in turn are excitations of underlying fields. What holds the table together is not a solid core, but a dynamic balance of interactions. Electromagnetic forces between atoms maintain structure. Quantum effects stabilize electron configurations. Fields interact continuously, yet maintaining the patterns that give rise to what we perceive as a solid object. In this sense, the table is not a thing in isolation. It is a process, a stable, ongoing pattern of interactions. This idea can be extended further. Even the atoms within the table are not static. Electrons are not orbiting nuclei in fixed paths like planets around a star. Instead, they exist as probability distributions, described by wave functions, constantly interacting with fields. At a deeper level, particles themselves are not fixed entities. They are excitations, temporary, localized patterns within fields that can appear, interact, and disappear. Nothing is truly static. Everything is in motion, even when it appears still. This leads to a different way of thinking about existence. Instead of focusing on objects as the primary units of reality, we begin to focus on processes. A process is something that unfolds over time. It is defined not by what it is made of, but by how it behaves, how it changes, and how it interacts with other processes. In this view, what we call an object is a relatively stable process, a pattern that persists long enough to be recognized, named, and interacted with. This perspective has been explored not only in physics, but also in philosophy. Alfred North Whitehead, for example, developed a framework known as process philosophy, in which reality is understood as a series of events and interactions rather than a collection of static substances. More recently, Karen Barad has proposed a related idea known as agential realism, which emphasizes that entities do not exist independently of their interactions. Instead, they emerge through relationships and processes. While these ideas are philosophical, they resonate strongly with the picture emerging from quantum field theory. Fields are continuous. Their excitations are dynamic. Interactions are fundamental. And what we observe as objects are patterns within this ongoing activity. This shift from objects to processes also helps explain how stability arises. If everything is in motion, why do some patterns persist? The answer lies in balance. Certain configurations of fields and interactions are stable. They can maintain their structure over time, even as the underlying components continue to fluctuate. For example, an atom remains stable because the interactions between its components are governed by precise rules that prevent it from collapsing or dispersing under normal conditions. Similarly, molecules form stable structures because of the way atoms bond through electromagnetic interactions. These stable configurations give rise to larger structures, which in turn can remain stable over longer timescales. A mountain, for instance, may exist for millions of years, even though the atoms within it are constantly moving, vibrating, and interacting. From a process-based perspective, the mountain is not a static object. It is a long-lived pattern, a pattern maintained by the interplay of forces, fields, and environmental conditions. This idea also applies to living systems. A living organism is not defined by a fixed set of particles. The atoms in your body are constantly being replaced through processes such as metabolism and respiration, and yet the organism persists. What remains is not the material itself, but the pattern, the organization of processes that defines the system. This reinforces the idea that identity, at a fundamental level, may be tied more to patterns and relationships than to substance. Returning to the concept of fields, this perspective becomes even clearer. Fields are always present. They evolve continuously. Their excitations form patterns that can move, interact, and persist for varying lengths of time. Particles, in this sense, are not objects travelling through space. They are events within a field, localized processes that can be detected and described, but not isolated from the underlying structure. This leads to a different kind of ontology, a way of describing what exists. Instead of a static ontology based on things, we move toward a dynamic ontology based on processes. Existence becomes something that happens rather than something that simply is. This may sound abstract, but it aligns closely with what we observe. Nothing in the universe is completely still. Even in the vacuum, fields fluctuate. Even in stable systems, interactions continue. Even in objects that appear unchanging, there is constant activity at smaller scales. This continuous change is not a disruption. It is the foundation. Stability emerges from motion, not from the absence of it. And as we become more comfortable with this idea, the distinction between objects and processes begins to blur. What we call objects are processes that are stable enough to be recognized. What we call change is the evolution of those processes over time. The universe, in this view, is not a collection of separate things. It is a continuous unfolding, a network of interacting fields, patterns, and relationships all evolving together. And within this unfolding, the familiar world emerges, not as a set of isolated objects, but as a tapestry of processes woven together in a way that gives rise to the appearance of solidity, identity, and persistence, a tapestry that is always in motion, even when it appears still. As we step back and look at the picture that has emerged, there is a quiet sense of both clarity and mystery. On one hand, quantum field theory provides one of the most successful frameworks in all of science. It describes the behavior of fundamental particles and their interactions with extraordinary precision. It allows physicists to calculate probabilities that match experimental results to many decimal places. It explains how particles arise as excitations of fields, how forces emerge from interactions, and how properties like mass can result from coupling to fields such as the Higgs field. And yet, for all its success, it is not a complete theory of reality. There are still open questions. Some of them are technical, involving the limits of the theory under extreme conditions. Others are more conceptual, touching on the very foundations of what the theory means. One of the most significant challenges is the relationship between quantum field theory and general relativity. Quantum field theory describes the behavior of fields within space-time, treating space and time as a given background. General relativity, developed by Albert Einstein, describes space-time itself as dynamic, shaped by the presence of mass and energy, and each theory works remarkably well within its own domain. Quantum field theory excels at describing the microscopic world of particles and interactions. General relativity excels at describing the large-scale structure of the universe, including the motion of planets, the behavior of stars, and the dynamics of black holes. But when we try to combine them, difficulties arise. At extremely small scales, such as those near the Planck length, which is roughly 1 divided by 10 followed by 35 zeros of a meter, the effects of both quantum mechanics and gravity become significant. In this regime, the smooth geometry of space-time described by general relativity may break down, and the probabilistic nature of quantum fields becomes essential. Attempts to describe this regime have led to the search for a theory of quantum gravity, i.e. several approaches are being explored. String theory, for example, proposes that the fundamental entities are not point-like particles, but tiny vibrating strings. These strings exist in higher dimensional spaces and can give rise to different particles depending on how they vibrate. Loop quantum gravity, on the other hand, attempts to describe space-time itself as composed of discrete elements, with geometry emerging from their relationships. Both approaches offer intriguing possibilities, but neither has yet been confirmed experimentally. This highlights one of the central challenges in modern physics. Testing these ideas requires energies and conditions that are difficult to achieve. The Large Hadron Collider, one of the most powerful experimental tools available, operates at energies of several tera-electron volts, which is an enormous amount by everyday standards. But the Planck scale, where quantum gravity effects are expected to become significant, is many orders of magnitude higher. This gap makes direct experimental verification challenging. As a result, much of the work in this area is theoretical, guided by mathematical consistency, indirect evidence, and the search for deeper unifying principles. Another open question concerns the nature of the vacuum. As we have seen, the vacuum is not empty. It is filled with fluctuating fields and zero-point energy. But when physicists attempt to calculate the total energy of the vacuum using quantum field theory, the result is vastly larger than what is observed in cosmology. This discrepancy, sometimes called the cosmological constant problem, remains one of the most significant unsolved problems in physics. It suggests that our understanding of the vacuum is incomplete. There are also questions about the interpretation of quantum mechanics itself. What does the wave function represent? Is it a physical entity, a description of information, or something else entirely? Different interpretations, such as the Copenhagen interpretation, the many worlds interpretation proposed by Hugh Everett, and relational interpretations, offer different answers. Each interpretation is consistent with the experimental predictions of quantum theory, but they differ in how they describe the underlying reality. This reminds us that even when a theory works extremely well, its deeper meaning may remain open to interpretation. Another area of active research involves the unification of forces. The Standard Model successfully describes 3 of the 4 fundamental interactions: the electromagnetic force, the weak nuclear force, and the strong nuclear force. But it does not include gravity. Efforts to unify these interactions into a single framework, sometimes referred to as a grand unified theory, continue to be an important goal in physics. Such a theory would reveal deeper connections between fields, showing how seemingly different interactions might arise from a common origin. There are also experimental challenges. Detecting new particles, measuring subtle effects, and probing extreme conditions all require advanced technology and careful design. Facilities like CERN, Fermilab, and other research centres around the world continue to push the boundaries of what can be observed. At the same time, as new approaches are being developed, quantum technologies such as quantum computing and quantum sensing may provide new ways to explore the behaviour of quantum systems and test fundamental theories. Astrophysical observations, including studies of cosmic background radiation, gravitational waves, and high-energy cosmic events, offer another window into the structure of the universe. These different lines of investigation complement one another, each providing pieces of a larger puzzle. And yet, despite all this progress, there is a sense in which the deeper questions remain open. What is the true nature of a quantum field? Why do the laws of physics take the form that they do? Is there a more fundamental level beneath fields and information? Or have we already reached the deepest layer, and what remains is simply to understand it more fully? These questions do not have immediate answers, but they are not signs of failure, they are signs of exploration. Science does not end when we find a successful theory. It continues, asking new questions, refining old ideas, and expanding our understanding. There is something quietly reassuring in this. The universe is not something we have fully grasped. It is something we are still learning to understand. And each step, each discovery, each new perspective adds to that understanding. At the same time, it is worth remembering that the theories we have developed are remarkably effective. They allow us to predict, to measure, and to explore the world with extraordinary precision. They reveal patterns and structures that would otherwise remain hidden, and they provide a framework within which we can continue to ask deeper questions. As we reflect on all of this, a certain balance emerges. On one side, there is knowledge, carefully built, rigorously tested, and deeply insightful. On the other side, there is mystery, not as something to be feared, but as something that invites curiosity. The two are not in conflict, they are part of the same process. And perhaps that is one of the most meaningful aspects of this journey. That understanding does not close the door, it opens it further. leaving us with a picture of reality that is both structured and open, both precise and expansive, a picture that continues to evolve quietly as we look a little closer